All right, hello everyone, and welcome to this RFMW and Marki Microwave webinar. My name is Katie, and I will be your Global Spec moderator today. Now I would like to introduce today's presenter. With us today, we have Harley Berman. Harley is the Product Marketing Manager at Marki Microwave. And with that, I'd like to pass things along to Harley to get this webinar started. So Harley, go right ahead.
Great, thanks Katie. Thanks everybody for coming. We're going to be talking about Filter Prodigy, which is our newest design tool today. This webinar is co-sponsored by RFMW, so thank you very much for that. So let's get right started. Imagine you're at work, and as usual, boss comes up to you, gives you an assignment. Today's assignment is to design a high dynamic range receiver. So, like all great designers that have come before you and in all of your previous successful designs, you do the same first step as always. You go to markimicrowave.com and see if there's been any new publications. You're in luck. So you find our first webinar, you went into the search and you searched webinars on receiver design. And you get this, Introduction to RF Front Ends for Direct Conversion RF Transceivers. Sip some coffee, enjoy the webinar, and you keep learning. Finish it, you got a lot of ideas going, but you need a little bit more. Go back to the web search, you're in luck, you found another webinar. This one was Design Considerations for High Dynamic Range Receivers. So at this point, you got all these ideas in your head that have come up from watching these webinars. You want to put some pen to paper, get some simulations going. So you find another webinar. This is the webinar on optimal simulation techniques for high linearity systems. At this point, you might have some initial block diagram that looks something like this. But I know there's many receiver designers on the call. You know that receiver design is not sunshine and rainbows like this. You are going to need many more filters than what we show here due to nonlinearities and interfaces between components causing spurs to pop up in band. So today, let's talk about filters. So a just high level look at the next 40 or so minutes. We'll start with a just brief discussion of the filters that exist in a system and Marki's filter capabilities. So both the types of filters we make, and importantly, I want to motivate the process technology we use. We're doing gas mimic technology, and explain why we are using this to develop Filter Prodigy. Now, Filter Prodigy is the main point of today's talk. This is our automatic filter design tool. So once we understand Marki's history, we'll talk a bit about how Prodigy works, and then we'll design a couple of filters today on the fly on the webinar. So without further ado, let's talk about what filters exist in a standard block diagram. And for the sake of this conversation, there's really only two types of filters that exist. Filters that were planned for, and what we'll call oh no filters. So planned filters are the ones we kind of talked about in the previous webinars. They can be large. This is because if you find a filter with the perfect performance, you can shrink other areas down to meet your swap goals. They can be COTS too. This is because since these filters are chosen early on, you can adjust your design parameters to support the perfect filter should it exist. And this is all because planned filters are chosen during frequency planning. That brings us to oh no filters. Oh no filters are kind of like a cleanup crew that comes in at the end and cleans up your spectrum of spurs and harmonics you weren't expecting. So these filters must be small. Ideally, they're as small as physically possible, because at this point, the board size and dimensions are already fairly rigid, and these filters were not designed in. So we need to somehow retrofit these in. So the smaller they are, the easier it is to integrate them. Additionally, almost always they have to be custom. They have to be custom because these harmonics are going to pop up somewhat randomly with a given pass bandwidth or cutoffs that you may not know until you physically measure it or do more robust simulations. And that is because all of these filters are chosen after frequency planning. Again, as the cleanup crew, they must be small and custom. So we have taken first steps to solving this problem a while back with the introduction of our new search tool on our website. We'll show this later. Essentially, it allows you to use a very familiar filter design interface, which is shown on the left, to plug in parameters you want, and then it searches our catalog for every single filter that may work. So for example, we're showing here, you may need a narrow passband and rejection far out. That doesn't necessarily mean you need a narrow band filter. A filter like this would work. We developed this tool sort of in line with just receiving so many filter requests for these oh no filters. On the right, we're showing just general Marki filter production over time. And you can see that these small form factor MMIC filters are really starting to take off. So that brings us to our capabilities. So what filters can Marki build, and why are we building them on a MMIC platform? I will start with addressing the promises of the MMIC platform, since that is what our automatic filter design tool, Prodigy, is based on. So without even going into Marki Microwave's proven history of successful first pass designs on a MMIC platform, just looking at MMIC in general, there are a few key advantages that it provides us, especially in terms of these small form factor custom filters. And the first one is called out in the bottom left here, which is that MMIC filters allow for you to achieve incredibly, incredibly small footprints. So what we're showing is comparison, a 2-scale comparison of MMIC on the QFN, the CSP, and the die, compared with something like thin film or laminate filters. There is just no comparison when it comes to optimizing swap. And then along the top are some of the other key differentiators of this technologies. Starting with predictability. MMIC lends itself very well to high quality simulations. So what we're able to do is provide simulated S parameters very, very early on in a design phase. And when the final filter is fabricated and parts are sent to you and you get them in your lab and you test them, you have an extremely high degree of confidence that the measured filter performance is going to overlap virtually perfectly with the simulated S parameters that you had received a long time ago. Going along with the predictability is the repeatability, and this is primarily just due to the etching tolerance of MMIC. It allows extreme repeatability both from unit to unit as well as lot to lot. So here in the middle, let me get them. In the middle here, there's the pointer, yeah. In the middle here, we see repeatability. So this is showing a handful of filters, all measured on die, and just showing how closely all of them overlap, including out here in the stop band, where even the ripple outside of the pass band overlaps. Just to clarify, over on this one, we're showing simulated and measured performance, but I'll show a couple more clear photos of that in a bit. The last major promise that I want to give of MMIC technology is the high frequency capability. Where a lot of technologies may drop off above maybe 50 gigahertz or so, MMIC filters operate very well all the way out to 100 gigahertz. So we have proven success with designing MMIC filters up to 110 gigahertz. Lastly, all this kind of comes together to allow us to build what we're calling Filter Prodigy, which is our design tool that allows us to interface with a real MMIC solving tool and achieve all the same predictability, repeatability, and high frequency designs virtually instantaneously. Now, before we get too deep into the promises of MMIC and before the Q&A box gets spammed with questions about Q, we can take a moment and comment on that. And yes, the Q of MMIC is not as good as some other technologies, such as thin film. That is okay. The reason being that there are several design tricks at our disposal on a MMIC that allows us to still achieve very low loss and very good rejection skirts. And additionally, we are seeing some trends within our customers that they will prioritize swap over Q for certain designs. Especially, an example would be if a designer knows early on that they can get these super, super, super small filters, but it's going to have 3 dB loss in the passband instead of 1. They can make trade-offs to accept the lower loss and fix that elsewhere in the chain in order to gain the extreme miniaturization. So all these promises of MMIC filters are well and good if we can build the filter for you. So a high-level look at our capabilities. We have a long history of the standard flavors of filters, so band pass, low pass, high pass, as well as diplexers. We've been releasing more MMIC diplexers and reflectionless filters. And I believe it was the end of last year that we started really investigating more exotic filter topologies and technologies. So we released recently a tunable filter. In a couple of slides, I will show more details on the tunable filter because it's similar to some other parts out there, and just to show where it shines and where it doesn't. However, all of this is to say, we have extensive history on a MMIC platform of designing any filter that you may use in your system, so long as it loosely falls within our standard capabilities. So you're going to get all the slides as a PDF at the end of the webinar. This is a great one to print out and just keep it at your desk for if you're ever looking for a custom filter, because this is on the middle column, we're showing our standard capabilities. On the right-hand side is our advanced capabilities. Essentially, this is to say, if you have a filter spec that lands within the standard capabilities, we can build it, almost certainly. Excuse me. Likewise, if you have a filter spec that lands more in the advanced capabilities or somewhere on the edges, we can still have a discussion about what potential trade-offs there might be, and we would love to at least hear what sort of filter specs our customers are dealing with and trying to achieve. So high level, if your center frequency is anywhere from 2 to 90 gigahertz, that's well within our wheelhouse. We aim for a typical passband insertion loss of about 1 to 3 dB. Many of our filters are below 2, and we have released a couple narrowband filters recently with sub 1 dB insertion loss in the center of the passband. And we also aim for, at 10% from the band edge, we aim for 40 dBc of rejection. These specs seem to be more or less in line with a lot of the filter specs that our customers are doing. Oh, and likewise, packaging, I did want to comment on. So all of these filters, including what we're talking about in Prodigy, they're all starting as die. However, we have extensive history of packaging our MMIC die in many different packages, all the way from 5mm QFNs to 1.5mm chip scale packages. Now here's just, I'm going to do 3 quick slides just showing off the sort of measurement accuracy, or excuse me, the simulation accuracy. The reason I want to show this is because Prodigy, the filter design tool we're going to show, it spits out S parameters to you. And this is more or less just to give you some confidence in the extreme agreement between S parameters provided by Marki Microwave for custom filters and the measured performance. And this is, I'm doing extreme cases here because these are actually packaged filters. So this is showing, essentially you would create a design, tell us you want it packaged. We would give you a packaged S2P file. So these are in, I believe these are in 4 or 5 millimeter QFNs. And we can see the dotted line for the measured performance and the simulated performance in the solid line. I mean, my screen might be too small, but I can't even see a difference here. I mean, there's minor variations in the return loss and the passband, but it's extremely close agreement. And this is, we're showing a couple different frequency points. So these are all packaged filters. And this is kind of what you can expect for our bandpass filters. We do have more advanced topologies that we briefly touched on. So in addition to fixed filters, which we have been making fixed filters for many years now. More recently, we've been moving to these MMIC fixed filters. Last year, we released our tunable filter. The tunable filter is very similar to the Atlanta Microwave AM. One of the Atlanta Microwave tunables. I wrote it down somewhere. Looking forward, we're doing some switched filter banks and then configurable multi-chip module type filters. Since I did tease the tunable filter and I mentioned Atlanta Micro, I will give them some credit. So here is comparisons of our tunable filter. We do have 3 out there right now. I just chose this one. And the Atlanta Micro AM3065. All right, there's the part number. So high level differences. So the x-axis on the bottom plots on the Marki ones, they are twice as long. So that's more or less just showing off the broader tuning range, and then the 2-scale packaging on the right showing a slightly smaller size. That is all true. The Atlanta Microwave part's not bad. So as all of you know, when you're doing a design, you make trade-offs. So there are trade-offs between these 2 parts. So for example, the low side rejection might be a little bit better in our part, but the high side might be better in theirs. Certain configurations of high and low side filtering, you might get better insertion loss in one versus the other. So I'm not trying to make the argument that MMIC is the only filter technology your receiver will ever need in the universe, because that's just not true. There are times where MMIC is the best, and there are times when other technologies are also the best. Again, you're gonna get these slides. So this is another good one that I think is decent to have by your desk, especially if you're a designer and you need some sort of high level, when do I want to use Prodigy versus when do I want to go get some custom cavity filter. So we're showing the different technologies along the top and performance parameters as each of the rows. Each technology is given a ranking from 1 to 5 in each performance parameter. So just some quick examples. If you need a very small filter, the best filter to get is going to be a MMIC filter. Likewise, if you need a very high frequency filter, like if you need a filter at 80 gigahertz, you're virtually limited to the MMIC filter as far as these types of filters go. If you want extremely low loss, super high Q, like brick wall type filters, you probably won't get a MMIC. You probably want something like a cavity filter. So this table is good to kind of absorb in your own time or print out and keep. I'm going to go through it in a more list type fashion where we call out when do MMIC filters shine and what scenarios might exist where they're completely smoked by the competition. So as we know, MMIC filters shine when the size must be small. If swap is your #1 concern or a tier 1 concern, you want a MMIC filter. Here we're showing a 2-scale drawing of our CSP package put on top of a dime, just so you have some frame of reference. It's a 1.5 millimeter square package. Additionally, when insertion loss is not a tier 1 concern, if you need some broadband filter and it's got to have 0.2 dB insertion loss, you might want to look elsewhere. If, on the other hand, you can plan for it early on and you want a high volume of filters, for example, then a MMIC filter would be great. When the rejection slopes can be achieved with 7th order or lower use of transmission zeros, and this is primarily just due to the limitations we have on MMIC, at Marki, we spend a considerable amount of R&D effort in developing our own topologies for MMIC filters that are Marki specific to Marki. So here we're showing just a couple. These are actually catalog filters, all of these. But you can kind of see the sort of trade-offs you can get in like a great zero on the high side, but looser roll-off on the low side, or good zeros on both sides, but more roll-off on the edge of the pass band. So again, it's all about trade-offs in this space, and the Filter Prodigy Designer makes performing these trade-off analyses, it makes it very easy to compare filters. Another time where MMIC filters shine, when the frequency gets higher, especially as it gets higher than 10 gigahertz, we have filters as low as 2, but it gets higher than 10 and up to like 40, 50 gigahertz, you really start to be limited in what other technologies can provide you in terms of frequency coverage, so just loss and reentrant mode suppression while maintaining good match and return loss. If volumes are high, MMIC filters are a fantastic option. They're printed on a wafer, so you'll get thousands of them if you want. And because of that, you can both have multiple designs on the same wafer. So if you don't need to have 1,000 of one filters. You could have 100 of 10 different filters, and you put them all on the same mask, and we can fabricate that for you. So if volumes are high, MMIC filters are great. If volumes are high and you wanted a bunch of cavity filters, good luck. MMIC filters are really good when power handling is low-ish. Low-ish, below a watt is fantastic. You'll have no problems. We have done more extensive power handling tests on our MMIC filters. We have seen power handling up to a couple watts, about 10 watts is where we're seeing some of ours start to break down. But power handling is a little bit squishy in that it does depend on, the thermal relief you can provide. It depends on if you're doing pulsed or CW. If you're doing pulsed, the type of pulse conditions. But this is all something that we at Marki would love to help you with if you have specific questions. If you want to see how a specific filter operates, you could always ask us, and we're happy to assist. When the signal chain requires high quality modeling. So when you need S parameters today for your design, and you can wait for us to fabricate it, but if you need S parameters today, MMIC filters are going to be a fantastic option. Because Marki has a very long proven history of MMIC designs, we have many, many products across the entire block diagram for a receiver that we fabricate on a gas MMIC substrate. We are able to integrate either in a die or co-package several of these MMIC devices. So here's just an example showing a theoretical LO driver integrated in the same package as a mixer and a filter on the IF in a single package. MMIC filters are also really good when reentrant modes are of concern. And this is because we have certain design tools at our disposal on a MMIC that allows us to more or less completely suppress reentrant modes. So this is showing a 30 gig filter out to about 80 gigahertz is where we had it characterized, and there's virtually no reentrant mode. Now, the opposite is true for when MMIC filters are just totally smoked out by the competition. So if loss is far more important than size, if you don't care about size, if you're fine with a big filter so long as you get almost no loss, then yeah, a MMIC filter may not be for you. If you need a one-off design, just the the business model is not really viable for very, very low quantity designs. If your filter specs do demand higher Qs, sometimes that is the case. Despite having tools at our disposal, there are times where you do need higher Q. And in those cases, for example, steeper rejection skirts, in those cases, you may not be able to go with a MMIC. And lastly, if you need super high power handling, again, up to maybe a couple of watts, maybe 10 watts is where I've seen some of ours start to break. They're fine. But if you need it to be a 100-watt filter for a transmitter, look elsewhere. And then lastly, if you need it to be very low frequency. So MMIC, we say low end is about 2 gig for our filters. We can maybe go lower if needed, but if you need maybe a 500 megahertz filter, you might even be able to just do a lumped element filter for something like that. So that's the end of just why MMIC, which is essentially best-in-class performance, size, repeatability, and scale. And then namely our ability to produce high-quality simulations that lead to a first-pass design success. Now, thanks all for staying with me. We've motivated why we've done MMIC filters. So what is this filter Prodigy? So let's talk about what filter design tools are out there for you. This here is the Marki complete suite of filter design tools. It's kind of ordered top to bottom as we get deeper and deeper and closer to a legitimate design. So we'll start with the LC filter tool. Really, LC filter calculator. This essentially takes all those equations you learned in school and spits out ideal numbers for ideal LC values to get you a filter. It's a good tool for low frequency filters. It's a great tool for low frequency filters, actually, in 100 megahertz range or maybe up to a gigahertz or two. But really, it's good to just see what's possible in the realm of filter design. If you can't make a filter using this tool, there's a chance it's not a realizable filter. So we go one step deeper, and that is the microstrip filter design tool. So this one is another calculator. It designs planar filters using ideal structures and ideal layouts. It works to a little bit higher frequencies, and again, it's a calculator, so it's going to give you exact lengths and widths. But there's no 3D modeling, there's no FEM simulations, there's no interfacing with HFSS. These top two are calculators. So that brings us to these bottom two. Hot Mess. Hot Mess is the driving force behind Prodigy. It is a proprietary filter solver. And this Hot Mess tool does integrate with HFSS, and this is where we're doing full 3D FEM filter designs. So no longer calculations, these are designs. This is an internal thing that we have at Marki, and it's basically the back end of Prodigy. Prodigy is what everybody on this call has access to. Prodigy is essentially the user interface for this, and this is what allows you to design filters on the fly, fully 3D modeled. And that is Prodigy. So it enables you as an engineer, as a salesperson, as an RF enthusiast, it enables you to design filters on the fly for these oftentimes low volume and high mix markets. So again, this is that case where maybe you have 15 different filters you need to clean up your receiver, but you need 5, 10 each of them. And you don't want us to design all these filters. This allows you to take the designing into your own hands. Because of that, and because of the interfacing with real design tools, it solves the problem of high accuracy in a low amount of time. And what all that does is it gives you, a designer, or what have you, the ability to do real-time system trade-offs instantaneously. Essentially, the whole goal of this is it slashes your time to market down, because you don't need to talk to us to design a filter. You can do a full design with incredibly high confidence that what you design in Prodigy is realizable. This is the business model that you are familiar with for MMIC filter design, custom MMIC filter design. You started by watching the webinars and creating a design. And then you have a filter spec that you want us to bid on and you want us to design. You send us the specs. We take your specifications, we take the information on, the project it's going in, how many you want to buy, what, how many times per year you're going to buy them. If it sounds good and it's got a decent business case, we'll go ahead and design it. And from scratch, we will design it. And we will give you the S parameters. You'll take those, put them in your system, and say, it looks all right, but maybe we have less roll off on the high end, and we can take some worse rejection on the low end. We say, sure, and we goes back to the start. New filter specs, again, new design, give it back to you. This cycle could happen, until you're happy, this cycle could happen before it finally jumps out of this blue box and into, we can build you a filter. And then we send our design off to get fabricated, and then we work on getting it over to you. This cannot work. This moving in the systems a lot of our customers are making, these next generation systems, they have extremely high channel counts, and varying different specs that they need for each channel and for each filter. Doing this sort of iterative design process with us doing the design every step of the way will slow you down in getting your product out the door. So this enables a new paradigm, which is Prodigy. Notice we only exist outside the box now. So inside the box is just you. You have a filter spec. You can go to Prodigy. Prodigy is, think of it as a super talented filter designer that is just crazy fast. You tell Prodigy what kind of filter you want, Prodigy designs you the filter. You take that S parameters. 2 minutes after it's designed the filter, you take the S parameters, drop it in your system. You like it, you don't like it, you go back into Prodigy, tell it what you want changed. Prodigy designs you a brand new filter. 2 minutes later, you get new S parameters. 15 minutes of doing this, and you may have a perfect filter. Click one button, submit for RFQ, and you've got our sales team roped in. They're ready to help you place this order. And that is exactly how Prodigy works. So this Prodigy was really motivated by this need for speed and solving the problem of accuracy versus time. A lot of our customers have wanted our filters, and they want these high accuracy models, but they don't have time for us to sit down and design a filter from scratch. So this is what Prodigy solves. You could do your own schematic level design, and it would be very fast. You could use the filter textbooks, you could use the filter tools, the calculators that we talked about, and you would get a very fast filter. And it won't be very accurate, unfortunately. For certain applications, that is. So then you might do the next best type of filter design. You might do a 2D model or a 2.5D model. This takes a little bit longer, but it's going to be a little bit more accurate. But still, you're not going to get S parameters as quickly, and you're not going to get S parameters that directly overlap with what you measure. The only way to get S parameters that will overlap what you measure is by doing the gold standard, which is 3D FEM simulations. And that is what HFSS does, or CST. So our goal is to be here. Everyone's goal is to be here, right? Highly accurate solutions instantaneously I think that would make everybody very happy. And we discovered a way to do that, which is through these design techniques and using the design techniques coupled with machine learning algorithms to really expedite the filter design flow. So here is Hot Mess. So remember, it was LC filter design tool, microchip filter design tool, Hot Mess. Hot Mess is an acronym, obviously. HFSS optimization through microwave element surrogate simulation. This is the back end of Prodigy, and this works well as a video, but I'll walk us through it. Essentially what's happening is Hot Mess starts with a topology. A lot of times this is a Marki proprietary topology that Chris invented. Takes a single topology and a single center frequency and a single percent passband. So that's what we're showing over here. All of these dots. Takes a single point, makes an initial guess, which is often suboptimal performance, and then it optimizes the performance in HFSS. After doing that for this point, moves on to the next point over, the next center frequency, and so on, until it creates a matrix of every possible center frequency that this topology can provide, along with every single passband that this topology can provide. This knowledge bank of known good filters is the secret sauce behind Filter Prodigy that allows us to do this instantaneous filter design. Make sure I'm on the right slide. All right, so here's the design flow. Starting with Hot Mess, we can generate these filter databases. So the way we just showed it, interfacing with HFSS, this is what takes time. We do actually do this for several topologies. You have access to Prodigy. That's what we're showing right here. Prodigy allows you to take arbitrary inputs and then through machine learning will interpolate between points to give you a real 3D design. So here's the status of Prodigy. It's live, it's on the website right now, and momentarily we're gonna go there and we're gonna play with it. Its initial release right now only supports bandpass die. We don't have packaged parts on Prodigy yet, but we will. And we only have 3 topologies, really 4 topologies, but as we'll see, one of the topologies is like a low and high band version of the same standard topology. Now, what we're showing today is Filter Prodigy as of March 12th. This is an ever-growing, ever-expanding tool. Directly in the pipeline, what we know we're going to add and what we really want to add are filter types, so low-pass, high-pass, and low-pass, high-pass combos, notch filters, what have you. The ability to support different requirements that you may have of your filters, and of course, adding packaging to Prodigy. So we model the die. We don't model package in Prodigy today. That is not to say we cannot package every single design in Prodigy. We can, but it won't be the instantaneous response that you get with Prodigy. And this kind of brings us to the next point. Prodigy is going to show you every possible center frequency and pass bandwidth that a given topology can create. That doesn't mean it's the best for that filter slot. Come talk to us. We likely can optimize. So with that said, I'm going to change my screen to screen sharing. We're going to go to the Marki Microwave website, and we are going to design some filters. So let me go ahead and share. Okay, I trust that you all can see the Marki Microwave website. So where is the Filter Prodigy tool? Where are all the tools? Well, up here in Technical Resources, you can go to Tools. There's a number of things under Technical Resources. This is also where you'll find device models and app notes, white papers, what have you. But today we're going to go to tools. Here's the Prodigy Designer. Before we go into Prodigy, I'm just going to quickly show what these LC filter design tools, the microstrip filter design tools, what they look like. So here's the LC filter design tool. It's a very standard, just LC circuit. But you can see, so it'll allow us to do, here, I'll change this to gigahertz, and let's see what happens if we do 25 gigahertz to 29 gigahertz compute. So it gives us a filter. This filter is not going to work. We're not going to get a 41.62 attofarad capacitor, and these lumped elements are not going to operate as expected at 30 gigahertz. So this tool is more just for showing what is possible in filter design, but you might not want to try and implement this. So let's go back to tools. The microstrip filter design tool is a similar user interface, so I think we can kind of skip it, because what we really want to show is Prodigy. This is filter Prodigy. So already, this is a real filter that we're looking at right here. I'm going to break down what we're looking at here, just so it's clear before we design. On the left, I'm going to zoom out too. We have 3 tabs. We have frequency and bandwidth, which allows you to change frequency and bandwidth. We have chart options, which allows you to change the display of the chart. And there's markers, so you can, do fine tuning checks within your filter's performance. Starting with frequency and bandwidth. This is where we keep our topologies. So I'm going to open that guy up. So topology 1, called Krabby, looks like a crab. So each of them have a nickname. They tell the type. And then here's where we get information about what the filter can achieve. So we know topology 1, Krabby, it's a bandpass filter. It's good for anywhere from 20 gig to 40 gig with 10 to 30% bandwidths. There's also a comment from the design team. So this is a 7th order filter with low and high side zeros, and very good insertion loss versus rejection. Then there's 2A and 2B, which is, as I said earlier, these are similar designs, just a low and high version. So the low band, they're both bandpass, type bandpass. The low band is the 7 to 18 gigahertz with a 10 to 40% bandwidth. The high band is 18 to 40 gigahertz with 14 to 40% bandwidth. So those are fairly similar filters. And then finally, we have Ringo. Ringo is another bandpass filter, which offers lower frequency, so 10 to 30 gigahertz and 5 to 20% bandwidth. So you can achieve lower percent bandwidths in this one. Additionally, the comment here, so this is a 6th order, capable of low percent bandwidths, and it can be modified for smaller footprint if needed. What's the footprint? How big is this filter? Well, down here, since these are full 3D models, we designed these in HFSS, we know the die size. So down here, we have the die size. Let's go ahead and design a filter. Let's say you need a filter that operates at 10 gigahertz and it has 18% bandwidth. So 10 gigahertz, we can't use Krabby 1. Nice, let's use the khaki low band. We can either move the sliders or just type it in. So I'll go ahead and type in 10 gig. Enter. Need it to be not much narrower, but maybe we'll bring it down to 18. At 20 gig, I really don't care about all this. I'd rather see what's going on here. Totally doable. we go charging. So this is S211 frequency. We don't care about the high frequency stuff. Let's cut this guy off. We want to see what the rejection is. So we'll draw here and here, and decent passband here. These markers are distracting. I care more about what happens between 9.5 and 10.5 gigahertz. So we go to markers, and we can just delete these. If I want to see something, I can add a new marker. So this is the first marker. The type of marker. So what do I want to look at? Do I care about insertion loss? Do I care about return loss? Am I just curious what happens at a given frequency? So for this, yeah, we'll say that. What's happening at 9.5 gigahertz? Well, we have we'll say 2.3 dB insertion loss and about 20 dB return loss. All right, that's decent for my spec. And let's say 10.8 is the second point that we care about. All right, so we see a little bit higher. What's that? 2.4 dB. Let's say we care about, I guess 10.8 was fine. 2.4 dB and then minus 21.2 return loss. This looks decent, but I really need to zoom in. I can't quite make out what's happening right in the passband. So we can go here. And keep in mind, every time we're doing these designs here, every time we change something, this is a full design. So let's go minus 10. Okay, let's zoom in a bit more. So let's start the frequency. Let's start it at 8 gig and go up to 11. Maybe 8.5? Yeah, nice. Okay, so we see 2.3 and then 3.4. This looks good. It's a decent size. This might work in my system. But I wanna see what else is out there. So it's just as easy as going back to the frequency bandwidth and saying what other topologies work. So we have Ringo. This will work for a 10 gigahertz, 18% bandwidth. Select Ringo. It maintains all of our same parameters. And we can see, oh, so we achieved better insertion loss actually at our high side. We can go back. So we went from 3.37 to 2.5. And then, if you wanted to see what does the rejection look like very far out of band, let's see it. Significant reentrant modes. So this allows you to perform immediate trade-offs instantaneously by just changing, what does this one look like out of band? Oh, the reentrant modes are a lot better. Do I care more about reentrant mode suppression at the expense of some loss? Or do I want better loss and I have a filter at the end that's going to deal with all of this? This is the type of stuff that we would be having in conversation with you. But now you can do all this immediately. You like the results? Just simply, nice. You can type in your email address. This is my email address. And submit an RFQ, email for an S2P. Or if you like it so much, you're ready, you could just submit for an RFQ. Say, thank you. Can you make it smaller? Also, can it have lower loss at the high end of the passband? You just put in your project. We'll put a random name, production start date. You're going to start November 10, random date, 2025. And you just fill in the rest of this information. And this goes directly to our sales team. You'll then get your S parameters and you can run with that in your system. Now, before we actually leave the Prodigy tool, and we will open for a Q&A, there's one other tool that we talked about today, which is, let's say you got no time. Filter Prodigy, great, fast. I'll use it for future projects. I need to see what's in stock today. That's been made extremely easy with our new filter search. So you can simply go to any of the package types. So whatever you're using for this, let's say we're doing a surface mount design, and go to fixed filters. And we're greeted with a very familiar filter design interface. This actually reminds me a lot of the LC filter tool. So let's say we need I think we said like 9.8 gig to, let's say, 10.2 gig filter. Let's ignore rejection requirements. Let's say we don't really have rejection requirements. All I care about is I can select this little passband here. I can select a response type. For this, I want a bandpass filter, so I want to select it. We'll start with any package type. All you do is hit search. Rejection. Oh, my bad. Let's say 8 gig. Two to 8 gig we care about rejection, and we'll say 20 to 30. All right, now let's see it. All right, my apologies. So now we see our entire catalog has been narrowed down to all these filters. Again, we can do real-time trade-offs. This is measured S parameter performance. So what you see is what you get. I want to see, oh, this is another filter. Very similar. I get some trade-offs here. What does this filter look like? If I like a filter, all I do is I download the S2P file right here, and I can add it to my system. So there's the MFBA 4 filter. If you didn't want to ignore the rejection requirements, you can put those back in, search again, and now we have rejection requirements in, and we can, again, look at what the filters look like. We can just choose any filter that we like. So that is the filter search tool. So this also streamlines your time to market and your ability to just search our catalog. What was that one webinar that we talked about in the beginning on simulation tools if you wanted to use these? If you forget, you can just use the search simulation webinar. Anything you want. We've recently updated our website, which has allowed for this great search. So you can search just keywords, whatever you like, and this is the webinar. So now I'm just showing off. We can go back and we'll do some Q&A on Prodigy itself. So the question was, how does the design tool run an HFSS simulation so quickly to spit out the S2P file? So that's a good question. The filter Prodigy is not running an HFSS sim. Hot Mess already ran HFSS simulations for every filter, for almost every filter within a given topology. What Prodigy does is Prodigy uses machine learning to interpolate between the points. So there is, once you get the S2P file that you like from Prodigy, there is still some, a Marki engineer still has to touch it. There's still some final layout, but what Prodigy enables is the extreme agreement between the simulated S parameters that we give and what you'll receive on hardware, because those S parameters are based on an HFSS sim. So thanks for that question. Does the Prodigy filter design tool design QFN package filters? If so, what QFN size do you use? So we touched on this briefly. No, we do not. We don't package the filters for Prodigy right now. Today, Prodigy is showing what's possible as a bare die. As you saw when we did the filter search, and as you probably know, we do package our filters in QFNs. Many of them are in, I think, 3, 4, 5 millimeter QFNs. If you like a design in Prodigy, if you've designed something and it works very well in your system, when you submit the RFQ, just write, can you package it? And we will almost certainly respond with yes, yes we can. And then again, I could go back to it. When we do get that request to package a filter, we will resim it with all the packaging effects. So we'll take into account the bond wire inductance and the parasitics of the package itself, and give you a new S2P file. It should match very closely to what you designed in Prodigy. If you liked what you designed in Prodigy, if you want us to make minor tweaks, we could do that. But these are two different packaged filters showing simulated, with package effects and measured. So this is kind of to give some confidence on what Prodigy can achieve when we do implement the packaged filters. Okay, so can you simulate temperature? So we only have 3 minutes, so this might be the last one. Can you simulate temperature performance? What sort of variation over temp and what sort of variation from unit to unit, lot to lot you expect from a filter designed with this tool? So unit to unit, lot to lot is a lot easier to talk about than temperature because this here, the middle one is showing exactly that, unit to unit, lot to lot. It is about as the repeatability of MMIC filters and repeatability of Prodigy design filters is going to be about as good as you can get on a filter technology. So the variation is going to be extremely, extremely low. Now, temperature performance is a lot more difficult to model and to include into Prodigy. Perhaps down the line, that is something that we could add the capability to. Right now, what we do offer instead on our website, we have a number of tech notes and application notes, including, I want to say 3 or 4 at this point, specifically on MMIC filters, including robust discussion of power and temperature performance. So you can see performance over temperature. So I'm going to go ahead and hand it back to Katie. Thank you so much, everybody, for sticking around and listening. There are many more Q&A questions, so I will get back to all of you via email. But with further ado, Katie, all you.
All right. Thank you so much, Harley. So we do have a ton of other questions, like Harley mentioned, that we did not have time for today. And Harley will get back to you when he can on any questions that have been asked. Thank you, Harley, so much for a great presentation and for an awesome demo. I think everybody really enjoyed it. So I just want to say a huge thank you to you before we end things today.
Yeah, thank you. And thanks, everyone, for coming.
So again, thank you all for taking time to attend our webinar event today. Take care, and we will speak with everyone soon.